Welcome to Statistics. Now I'm just going to give a brief overview of how we can use statistics in analytical chemistry. I'm going to assume that you have at least some knowledge of the statistics that I'm talking about. If you don't, then you're going to have to take some additional time, go back and review some statistics, or give yourself a better in-depth introduction into the statistics that we're going to use. So first let's talk about Gaussian distributions. So if you repeat an experiment a large number of times and the errors are random, we don't have any systematic errors, then the results will form what we call a Gaussian distribution, a bell curve. Now what we call a Gaussian distribution is also sometimes called a normal distribution, or also sometimes a bell curve. And this is a smooth bell-shaped distribution that we can see down here that's formed from a very large number of randomly distributed data points clustered about the mean. So here we've got basically a histogram showing the value that we obtained in our measurement, and the vertical axis here tells us how many data points we have at each of those values. Now this could be anything. It could be the sum of rolls on two dice, it could be the heights of people, and so on. Now it's impractical to repeat an experiment so many times that we obtain a Gaussian distribution. Instead, we typically perform an experiment somewhere between 3 and 5 times, and then use a statistical analysis to estimate the parameters for a large set, the population of all of the times we could have run that experiment. In other words, if we run an experiment an infinite number of times, then we won't have this sort of stepped structure to our distribution. We'll instead have the curved structure, that nice smooth shape. But we don't need to get that smooth shape in order to get an idea of what the true mean really is and what the standard deviation is. If we instead perform a sufficiently large number, we can get close enough to knowing probably with some degree of confidence what is the true mean and what is the true standard deviation for the population. So let's talk about mean and standard deviation. The mean, also called the arithmetic mean or the average, is the sum of the measured values x divided by n, the number of measurements. So we can write that out mathematically like this. We say the mean, or symbolized as x bar, is equal to the sum of all of our x values, all of our measurements, divided by n, the number of measurements that we have. Now the standard deviation, which we symbolize with a lowercase s, measures how closely our data are clustered about the mean. And mathematically, that is, s, the standard deviation, is equal to the square root of the sum of the differences between our values and the mean squared. So we take the difference between the first value and the mean, we square that. Then we take the difference between the second value and the mean, we square that and add it to the first one, and so on for all of our values. And then we divide by n minus 1. Now this n minus 1 here is what we call degrees of freedom. That's our quantity n minus 1. And so the more data points we have, the larger n minus 1 is going to be, because the larger n will be. And that means that the smaller our standard deviation will be. Another way of thinking about this is the more samples we take, the more measurements we take, the more confident we can be that our average is, in fact, at least close to the correct, true average value. The more samples we take, the larger our degrees of freedom will be, the smaller our standard deviation becomes. The smaller the standard deviation is, the more closely together our data points are lying, indicates how well we think that the average is close to the true value. In other words, if we have a very, very narrow distribution, then all of our data points are clustered very close together, and that means that we can be pretty confident that our average is pretty close to the true value. On the other hand, if our data points are really spread out, then our standard deviation here is going to be very large. This could also happen if we only have 1 or 2 data points. If you only have, say, 1 data point, then n minus 1 is 0. And that means that you don't have a standard deviation. You can't have a standard deviation of a single data point, because how close together is one data point to itself? It doesn't really make sense. So you can't really perform a standard deviation calculation on just one sample. Now note that for a population, this is a data set containing every possible data point For that population, the mean is symbolized with this symbol, mu, and the standard deviation is symbolized with the Greek letter sigma, the lowercase sigma. Now, the mean and standard deviation of a sample of the population are symbolized with x bar and s, respectively. And since we virtually never can sample all of a population in chemistry, we rarely use mu and sigma. Now, in other disciplines, you could potentially sample all of the population. For example, if you were, say, measuring the heights of everyone in a class, and if you had everybody together in one spot, then you could measure each individual person, and then you'd have the heights of each individual person in the class. On the other hand, if you're looking at, say, a larger number, instead of, say, 15 or 20 people, if you were trying to figure out what is the average height of people in the country, then you wouldn't measure every single person across the country. Instead, you would measure the heights of some people, and as long as you have a representative sample, meaning they're basically randomly picked from the entire population, then it's reasonable to assume that the average of your sample is pretty darn close to the average for the entire country. Now, this is obviously going to depend. If you only pick 10 or 20 people, you're pretty likely to have a skewed sample. For example, if I were to pick my students are not necessarily representative. My students are all younger people. As people age, they may get shorter over time. On the other hand, if we pick students that are very young, that haven't stopped growing yet, then they're likely to be shorter than the average person. So these are two different averages or means. In the first case, where I'm talking about what is the average height of students in my class, that I can actually sample each individual student. If I only have 20 students, it's a matter of measuring 20 people's heights. And in that case, we would symbolize that average with mu, and we would symbolize the standard deviation of those heights as sigma. On the other hand, if we're taking a sample to try to figure out what is the average height across everybody in the country, then the average of our sample we're going to symbolize with an x bar, and the standard deviation of our sample we're going to symbolize with a lowercase s. So now let's look at variance and how it's related to the standard deviation. The variance is the square of the standard deviation. And the relative standard deviation is the standard deviation expressed as a percentage of the mean. So 100% times the standard deviation divided by the mean will give us our relative standard deviation. Now, since the standard deviation gives us some idea of the uncertainty in our mean, then we can commonly express the mean and standard deviation as x bar, the mean, plus or minus the standard deviation, and then in parentheses we write the number of data points. We may round the mean to the first digit in the standard deviation and round the standard deviation to its first digit as an approximation for significant figures. As an aside, this brings up my favorite sentence in the book: try not to go into cardiac arrest over significant figures when you see 823.2, where this 2 is subscripted, plus or minus 30.3 as the answer to a problem in this book. That is, the author here is not going to be using significant figures perhaps the way that you learned them in general chemistry, and this is because significant figures is just sort of a hand-wavy way of keeping track of error. Here we're actually going to keep better track of error, and in the case of sampling or measurements, we're instead going to use standard deviation as a way of describing how much error there is in our measurement, or how much possible error there is in our measurement. So now let's discuss how the standard deviation relates to probability. Now, the formula for the area under a normal curve, a Gaussian distribution, is given here. So we've got y equals 1 over sigma, remember that's the standard deviation of the population, times the square root of 2 pi times e to the minus quantity x minus mu squared all over 2 sigma squared. Now that looks complicated, but that gives us a curve that looks something like this. And note that in the middle here, we've got mu, that's the average or the mean of our population. And then we've got these lines at minus 1 sigma, plus 1 sigma, minus 2 sigma, plus 2 sigma, and so on. So at -1, +1, -2, -3, and so on, of our standard deviation. So from the mean, plus and minus, one standard deviation, that's this area in here. On each side of the mean, within one standard deviation of the mean, we have roughly 34.1% of our population. And that means that from the mean, plus and minus, one standard deviation, we've got 68% of our population. So over 2/3 of our population is within one standard deviation of the mean. Then between one standard deviation and -1 standard deviation and -2, we've got another 13.6. So doubling that from -2 standard deviations of the mean to +2 standard deviations of the mean, we have about 96% of our population. And then ±3, we have even more. So ±3 gives us about 99.7% of our population. So if you have some data points that are outside that, those data points are pretty far out there. Now, as you saw on the last slide, it's often useful to express our deviations from the mean in terms of multiples of the standard deviation. And that's what we call z, or the z-score. So the z value is equal to x, our data point, minus the mean divided by the standard deviation. Likewise, we can write that instead of for our population, we can instead write that for our sample. So x minus x bar divided by s, or our value minus the average divided by the standard deviation. Now, the probability of measuring z in a certain range is equal to the area of that range under the normal distribution. For example, the probability of observing z between 1 and 2 times sigma is 0.136, or 13.6%. So in this way, the standard deviation is a measure of the width of our curve. That is, the distance from here to there. Well, really the distance from one of these points to the mean is our standard deviation. The distance from one point to the other is twice the standard deviation. Now, I encourage you to visit this link or just search on Wikipedia for z-table. Now, in Wikipedia, they're going to call it the standard normal table. It's often called the z-table in statistics books. Now, if you scroll down, you then get to this table full of values. Down the left side, you've got the first 2 digits. So it starts with 0.0. Underneath that is 0.1. So you've got the ones place and the tenths place. On the top, you've got the hundredths place. So if you're looking for, say, a z-score of 0.27, you come down to 0.2, and then you scroll over to 0.7, and that's this value here. So that's 0.10642. And that gives you the probability that your statistic, your sample, is between that z-score and the mean. So for z of 0.27, we had 0.10642. That's 10.6, roughly, percent. We have a 10.6% chance of our z-score of any sample that we take being between the mean and a z of plus 0.27. That's only a quarter of our standard deviation. If we go to 1.0, that then gives us 34.13. That's where that 34.1% of our samples are going to be between our mean and positive z.1, basically between the mean and the mean plus 1 standard deviation. Now you'll have the same proportion between the mean and negative 1 standard deviation. So this is not giving you a cumulative value of between the mean and plus and minus 1 standard deviation. So you'll need to double these values if you're looking at plus and minus. So suppose that we want to determine the lifetime of light bulbs. We could select one light bulb at a time and measure its lifetime. Now that's going to take a really long time. Or we could select 4 light bulbs at a time, measure their lifetimes, and compute the mean of those 4. Now, the mean of many sets of 4 light bulbs is the same as the mean of the population. That is, the mean of many individual light bulb samples. However, the standard deviation of the sets of 4 light bulbs is smaller than the standard deviation of the population. Now, because we expect random errors to cancel, at least partially, then the mean of a sample of 4 bulbs is likely to be closer to the mean of the population than the individual light bulbs. Now, the standard deviation of a set of n values, sigma sub n, is related to the standard deviation of individual values, sigma, by this equation, where we have sigma sub n is equal to sigma divided by the square root of n. That is, the uncertainty in the mean of a set of samples decreases as a factor of the inverse of the square root of n, the number of samples that we have, So to decrease the uncertainty by a factor of 2, you must collect 4 times as many measurements. To decrease the uncertainty by a factor of 10, you have to collect 100 times as many measurements. And so clearly, there's diminishing returns here. It's worthwhile to be twice as certain in our value to take 4 times as many measurements in most cases. But it might not be worthwhile to take 100 times as many measurements. And so at a certain point, you go, good enough. We're confident enough in our value. So now let's talk about confidence intervals. A student's T is a statistical tool that's often used to find confidence intervals and compare results from different experiments. From a finite set of measurements, we cannot obtain mu or sigma, because remember, those discuss the population mean and standard deviation. Instead, we obtain x bar and s. Now, we can then calculate a confidence interval within which we are certain, to some level of confidence, contains mu, the population mean. That is, we're going to take our sample average, our sample mean, and compute some interval around that at which we are, say, 90% certain or 95% certain that the population average is within that interval somewhere. Now, obviously, the more samples we've taken and the smaller our standard deviation, the lower or the smaller that interval is going to become. Now, the confidence interval is equal to x bar, our sample average, plus or minus our t value, times s, the standard deviation of our sample, divided by the square root of n, the number of samples that we have. So again, I encourage you to either visit this link or search Wikipedia for students' t distribution. And again, you get a long article here. But if we scroll down, we eventually get to, way down here, we get to another table. And so now you see at the top, we've got one-sided and two-sided and then a bunch of percentages. These are the confidence. So if you want to be, if you're doing, say, a one-sided and you want to be 95% confident, then you're going to be in this column here. And down the left side, you then have your number of degrees of freedom. Now typically, these tables start out with degrees of freedom incremented by 1, so 1, 2, 3, and so on. But at a certain point, they're then going to start skipping values because the difference between, say, 50 data points and 60 data points is relatively small. You'd always want to use the smaller of those two. So you find the number of degrees of freedom, you go over to your confidence interval. So let's say we took 4 data points and we want to be 95% certain, then our t value here is going to be 2.132. So if we go back to our equation here, our t value, that 2.132, is what we're going to plug in here for t. So we'll have a confidence interval of our mean, plus or minus 2.132 times our standard deviation, divided by our number of degrees of freedom, which if we had 4, would then be the square root of 4. Now, we can use a t-test to compare two means to determine if there is a statistically significant difference between those two means. Now, the null hypothesis states that there is no difference between our two values. Note that we cannot ever prove the null hypothesis is true. The only thing we can do is disprove it. That is, we can show that it's false. We can't, however, prove that it's true. So the null hypothesis is similar to the US legal system. The accused person is assumed to be innocent, and the prosecution must present compelling evidence that the accused is guilty in order for us to reject the null hypothesis, that the accused is innocent. That is, if there is reasonable doubt that the accused is guilty, then the null hypothesis, that that person is not guilty, cannot be rejected. In other words, only if there is no reasonable doubt, that is, we are absolutely certain, or that jury of peers, which in the US is 12 people, if 12 people unanimously agree this person is guilty beyond reasonable doubt, I have no doubt that this person is guilty, that's when our legal system says the person is guilty. If one person says, no, I can't agree, I don't think this person is guilty, we either get to a hung jury or that person is decided to be not guilty, which doesn't mean that that person is innocent. So in the US legal system, we never prove a defendant to be innocent. Instead, we say the jury found the accused not guilty, or found the accused innocent. Usually we say found the accused not guilty. And this only means that there wasn't enough evidence to convict the person. There wasn't enough evidence to conclude that that person was in fact guilty. We're not saying the person didn't commit the crime. What we're saying is we don't have enough evidence to find that person guilty. Likewise, in science, we never really prove the null hypothesis. We're assuming from the get-go that the null hypothesis is true, and we need to have enough evidence to reject that null hypothesis. In other words, we need enough evidence to conclude beyond a reasonable doubt that the null hypothesis is not true, that our alternate hypothesis might be true. But again, we're not proving the alternate hypothesis true, we're just disproving the null hypothesis. So the t-test tells us the probability that the observed difference between the two means is due to random error. Now we reject the null hypothesis if there is less than a 5% chance of the difference being due to random error. And this gives us a 95% confidence in our result. Now you could use different values here. You could say less than a 10% chance, and that would then give you a 90% confidence, or so on. If you need to be more confident in your result than 95%, then you're going to use a smaller value here than 5%. But in general, certainly for this class, 95% confidence is pretty good. That means there's only a 1 in 20 chance that you're wrong. So let's look at 3 different cases that are handled differently. In the first case, let's say we measure some quantity multiple times and we obtain an average and standard deviation for that sample. We then want to compare our value with an accepted value, one that we know is true. So our average is not the same as the accepted value, but does it agree with the accepted value within experimental error? In the second case, we measure some quantity multiple times by 2 different methods. We have now 2 averages and 2 standard deviations. And we want to know, do our results agree with each other within the experimental error? In the third case, we have a number of samples designated, say, A, B, C, and so on, up to n, however many samples we have. And we measure each sample once with method 1 and once with method 2 and obtain different values. Do our results agree with each other within experimental error, or do they disagree? That is there some significant difference between our 2 methods of measuring? Now, this is different than the top case, because in the top case, we're measuring one quantity many times with our 2 different methods. In the second case, we're measuring different quantities, samples A, sample B, sample C, and so on, once with each of our measurement techniques. So let's look at that first example, comparing a measured result with a known value, something that is accepted to be true. So suppose we purchase a coal sample certified by NIST to contain 3.19% sulfur, and we want to test a new analytical method to determine if it can reproduce the value provided by NIST. Now the measured values, let's say, are 3.29, 3.22, 3.30, and 3.23% by weight of sulfur, giving a mean of 3.260 and a standard deviation of 0.041. So we want to know then, does our method agree with NIST? Now we have 4 measurements, which gives us 3 degrees of freedom, because remember it's n minus 1. Now from the t-table, at 95% confidence, we get a t-value of 3.182 for 3 degrees of freedom. And thus, our 95% confidence interval is x bar our mean. So we have our mean, 3.260, plus or minus our t-value, 3.182, times the standard deviation of 0.041, all divided by the square root of n. And that then gives us 3.260 plus or minus 0.065, which is 3.195 up to 3.325. Now, that NIST value of 3.19 is outside of our confidence interval, so with 95% confidence, we can say that our method does not agree with the NIST value. Now, bear in mind that because the NIST value is just outside of our confidence interval, it's probably a good idea to take some more measurements. Now, remember, we only had 4 measurements, and it probably makes sense to go back, take some more measurements, and then redo our calculation now that we have more measurements and thus more degrees of freedom, and see whether the NIST value is still outside of our confidence interval. Now let's look at that second example of comparing replicate measurements. Now, Lord Rayleigh received the 1904 Nobel Prize for discovering argon. Rayleigh removed all of the oxygen from dry air by passing the air through hot copper to make copper oxide, and then measured the density of a fixed volume of the remaining gas, now at fixed temperature and pressure. He also produced pure nitrogen by decomposing nitrous oxide into a nitric oxide or ammonium nitrite. And so here we've got a table. This is table 4.3 from the book. This table shows Lord Raleigh's measurements from air and from chemical decomposition. And so you can see that he got this difference here. The average mass left over from that volume of air was 2.31011 grams, and from the chemical decomposition, he got 2.29947, and they're both plus or minus some standard deviation. So Rayleigh has two means, two standard deviations, and he wants to see, are those two methods significantly different? Here we have two measured results with no known value, or no accepted value. Now we can calculate a value for t using this equation. We've got our t value that's calculated as equal to the absolute value of the difference between our two means, that is x bar 1 minus x bar 2, divided by this S pooled. S pooled is the pooled standard deviation, and I'll get to that in a minute, times the square root of n1 times n2 divided by n1 plus n2. So this S pooled is a pooled standard deviation using both of our data sets. And that's equal to this equation here, which is the square of the standard deviation of our first sample times the degrees of freedom of our first sample plus the square of the standard deviation of our second sample times the number of degrees of freedom of our second sample divided by the sum of the number of measurements in each sample, so n1 plus n2, and then minus 2. And we can then compare our calculated t value against the t value for our number of degrees of freedom, which is n1 plus n2 minus 2. And so using Lord Raleigh's measurements, when we plug in the values, we then get a pooled standard deviation of 0.00102, and our t calculated is then 20.2. So for 13 degrees of freedom, the t value from the table lies between 2.228 and 2.131 for 95% confidence, and thus our t calculated is larger than our t table, and we can reject the null hypothesis and conclude the difference is in fact significant. That is, Raleigh's samples from air have a higher density because they contain something other than just nitrogen. They contain argon, which of course would not react with the hot copper. And obviously argon is heavier than N2. So now let's look at our third example, a paired t-test for comparing individual differences. So suppose we have a number of samples designated A, B, C, and so on up to N. You could just as easily use numbers here as we have in this table here. And then we then measure each sample once with method 1 and once with method 2 and obtain different values. Do our results agree with each other within experimental error? So here we have a spreadsheet showing our sample number. We've got method 1 and some measurement. We've got method 2 and some measurement. And then in the third column, we've got the difference between method 1 and method 2. So sometimes you can see method 1 is higher, and so we have a negative difference here. Sometimes we have method 2 is higher, so we have a positive difference, and we can then average these difference values. Now remember, in this case, each sample has been analyzed a single time with each method, once with method 1, once with method 2. No measurement has been duplicated. That is, we haven't measured sample 1 with method 1 more than once. We only measured each sample once with each method. Now, to determine whether there is a statistically significant difference between the two methods, we can use what's called a paired t-test. Now, we first calculate the difference between the two methods for each sample. That was that third column. We're going to symbolize this with a D, or a D sub, and then whatever the index is. We then calculate the mean and standard deviation for our difference values. The standard deviation for the differences is calculated by this equation. So S sub D, the standard deviation of our differences, is equal to the square root of the sum of the difference between our difference value for whatever sample we're looking at minus the average difference, d bar, squared, so we're summing the squares of those differences, divided by n minus 1, which in this case gives us 6.748. We can then calculate our t value using this equation. So t calculated equals the absolute value of the difference divided by the standard deviation of our differences times the square root of n, which in this case then gives us 1.224. Now the value for t from our table at 95% confidence for 10 degrees of freedom is 2.228. And since our t value here is less than the t value from the table, we cannot reject the null hypothesis, and thus we cannot conclude that there is a significant difference between the two methods. That is, there is a greater than 5% chance that the difference observed between the two methods is due simply to random error. So now let's look at outliers. One way we can test for outliers is using the Grubbs test for an outlier. So suppose we dissolve zinc from a galvanized nail and measure the mass lost in order to determine the percent of the nail's mass that was zinc, and we obtain 12 results. We've got 10.2, 10.8, 11.6, 9.9, 9.4, 7.8, 10.0, 9.2, 11.3, 9.5, 10.6, and 11.6. Now, there's one value that appears different from the others, this value at 7.8. All the others are clustered between 9 point something and 11 point something, but this value is less than 8. So we can test whether this point is an outlier using the Grubbs test. So we get our g value, our Grubbs value, is equal to the absolute value of our suspected outlier minus the mean. That is the difference between our value and the mean, the absolute value of that difference, divided by the standard deviation. In other words, how many standard deviations is this value away from the mean? Which in this case gives us 7.8 minus 10.16 divided by 1.11, which is 2.13. So our value is 2.13 standard deviations away from the mean. Now note that the mean and standard deviation above include our suspected outlier. You have to include that suspected outlier. Now, if our calculated g value is larger than the g value from our table, then we say that data point is in fact an outlier and we can discard it. If it's not, however, we cannot discard that data point because it's not an outlier. So in our example, our calculated g value is less than the g value from the table, which was 2.234, so we cannot discard our value. That is, there's a greater than 5% chance that the data point is part of the same population as the other values. Remember that with a normal distribution, you'll have a small percentage of your population outside of that, say, window of plus or minus 2 standard deviations from the mean. You'll still have a few percent outside of that. Now, if our calculated g value was, say, 7, we're 7 standard deviations away from the mean, that's pretty far out there. We're pretty unlikely to have a data point that's that far out, and thus that data point probably is in fact an outlier, and we can go ahead and remove it. Now, note that you should use some common sense in removing a suspected outlier. If you know that you spilled part of the solution for the suspected outlier, then you should eliminate that data point. Realistically, you should have eliminated that data point as soon as you made that spill. You need to start that particular trial over again. So you know the data point involving the spill is not part of the same population as your other values. Your other values didn't have a spill in them, and thus you're measuring different values. When we perform most chemical analyses, we use a calibration curve to compare our measurement against measurements of known quantities of analyte. Now, we use the method of least squares to draw a calibration curve, which is usually a straight line, through our data points for the standards. Now, in this procedure, we assume that the errors in the y values are much higher than the errors in the x values. That is, we're more confident in where those data points lie on the horizontal axis than we are on the vertical axis. And we assume that the uncertainties in all of our y values are similar. Now, we draw a straight line between our points such that the vertical deviations, those deviations in y values, are minimized. So in this case, we get something like this, right? We've got all these blue data points all over the place, and we minimize the vertical distance between our data point and the line, the red line. So we're not minimizing the distance in x direction because we're assuming that our data points are in the correct place left and right, but just perhaps the incorrect place up and down. Now we can calculate an uncertainty to be associated with our line of best fit, and I'm not going to go into that here. You can see the book for how to do this. Generally, if you're using a computer to make your plot, which most of the time you would, the computer will perform the calculation for you. Most of the time it's going to be an R² value. This is basically how confident the computer is that that is in fact the line of best fit. That R² value gives us an indication of how well our data points fit that trend line that we see. So the closer our data points get to that trend line, the larger that R² value is going to be. It ranges between 0 and 1, so the closer that value is to 1, the more confident we can be that that equation, that trend line that we have, is in fact the correct trend line. And that was statistics.